Hello again. This is Math 2115 coming to you from the College page, and this is the conclusion of the lecture entitled Mathematical Relations. And consider these examples as illustrations of the kind of problem I could ask on a test or a quiz, and other examples are in the assigned homework problems. So let's get to it. Okay, so let's talk about the less than relation for real numbers. So we define a relation L from R to R as follows. X, L, Y, if and only if X is less than Y. And this is for all real numbers because they have R and R. So the question is 57 L 53? That means is 57 less than 53? No. 57 is bigger than 53. Is minus 17 less than minus 4? Yes, because minus 17 is less than minus 14 is to the left on the number line. Is 143 less than 143? No. 143 is equal to 143, not less than. And is minus 35 less than 1? Yes, because minus 35 is to the left of 1 on the number line. And in part E, we're to draw a graph of L as a subset of the Cartesian plane R cross R. So this is the x-axis, this is the y-axis. So this is the set of all points where y is bigger than x. So here's the line y equals x. Now points on that line are not included because it's dotted, but everything above it is. So that is the shading of that relation. Let's talk about a different kind of relation. This is the congruence modulo 2 relation. So we're going to define a relation E from the integers to the integers as follows. For every mn, an element of z cross z, we say that m, e, n, if and only if m minus n is even. Now this is saying that it has the same remainder when you divide by 2. But anyway, so let's look at some questions then. Is 4e 0? Is 2e 6? Is 3e minus 3? Is 5e 2? Well, the answers are 4e 0, yes, because 4 minus 0 equals 4, and 4 is even. That's the definition that we have up here. 2e 6, yes, because 2 minus 6 is minus 4, and minus 4 is an even integer. 3e minus 3, yes, because when you subtract the 2, a minus is a plus, so that is 6, and 6 is even. But no, 5 is not e2, because 5 minus 2 equals 3, and 3 is not even. In B, we're asked to list 5 integers that are related to, by E, the relation E, to 1. And there are many examples here, but we pick 1, 3, 5, minus 1, and minus 3 as our example, and here are the reasons why. Now here, we're asking you to prove something, and again, we do proofs in this course. So prove that if n is any odd integer, then n is e1. Well, so suppose n is any odd integer, then we know that n is equal to 2k plus 1 for some integer k. Now by the definition of e, n e1 if and only if n minus 1 is even. So n minus 1 is equal to, but n was 2k plus 1, so we subtract that as 2k. And since 2k is an integer, 2k is even, hence n e1 by definition. That is what's to be shown. And this is the same thing really as saying these m and n are congruent mod 2 that we talked about before as a function in one of the previous lectures. Let's talk about an example of the inverse of a finite relationship. So we have a set A is 2, 3, 4, B is 2, 6, 8, and let R be the divides relation from A to B. So X, R, Y, if and only if X divides Y. That's how you read this, this bar in this case. So we're supposed to state explicitly which ordered pairs are in R and R inverse. And then we're to draw arrow diagrams for R and R inverse. Okay, let's talk about that. So when we're talking about, we're saying which ones divide. So 2 divides 2, 2 divides 6, 2 divides 8, 3 divides 6, and 4 divides 8. So you see that's a complete listing of R as defined up here. Now R inverse, what we do is we just switch the X's and Y's, and we get this as our set. If we draw an arrow diagram, now this is an arrow diagram, this is not necessarily a digraph, and this is not a digraph, but we see that this is showing about the relation R, and so we have these arrows. 2 is related to 2, 2 is related to 6, and 2 is related to 8, and so on. So this is that, and if we just draw the arrows in the other direction, we have the inverse. Describe R inverse in words. R inverse can be described as, for every ordered pair YX, an element of B cross A, X R inverse Y R inverse X, if and only if Y is a multiple of X. Now, we were doing finite relations, but we actually can have the inverse of an infinite relation. So, define a relation R from R to R as follows, and is for every ordered pair XY in R cross R, X is related to Y, or X RY, if and only if Y is equal to 2 times the absolute value of X. And draw graphs of these in the coordinate plane and answer the question, is this a function? Well, the graph of, in the real plane, the set of xy such that y is equal to 2 absolute value of x is this curve that you've graphed many times. And this is a function because it passes the vertical line test. This is not a one-to-one function because it does not pass the horizontal test, and it's not an onto function because no negative numbers are achieved by this function. Now, if we switch the x and y, we get this, and we see that, oh, this is not a function because it does not pass the vertical line test. Let's talk about some examples of having you come up with directed graphs of a relation. So suppose we have this. A is these numbers 2, no, it's 3, no 2. 3, 4, 5, 6, 7, and 8. And the relation is defined on the A as follows. For every xy that are in set A, x is related to y if 2 divides x minus y. You have to think about what this means. We're to draw the diagram. Now note that 3 is related to 3 because 3 minus 3 is 0, and 2 is divided into 0, since 0 is equal to 2 times 0. So there is a loop from 3 to itself. And similarly, there's a loop from every number to itself. Note that 3 are 5 because 3 minus 5 is equal to minus 2, and minus 2 is 2 times minus 1. And 5 are 3 because 5 minus 3 is 2, and 2 is 2 times 1. So we do have an arrow from 3 to 5. So here is 3 to 5, and we have an arrow from 5 to 3. And so we can check to see these other arrows are obtained by similar reasoning. And I could ask you this kind of thing, asking you to draw a graph and fax the PDF, not fax, scan the PDF in and up. Let's look at some additional properties of relations on finite sets. So suppose A is this, And we define relations R, S, and T on the set A as follows. So R is this set of ordered pairs, S is this set of ordered pairs, and T is this set of ordered pairs. And we ask the questions in turn. Is R reflexive, symmetric, and transitive? Is S symmetric, reflexive, and transitive? And is T reflexive, symmetric, and transitive? Okay, let's, and in this case, it's probably easiest to talk about a digraph of R, and so the digraph of R looks like this. Now you can tell it's reflexive right away because there are loops on each of the vertices, so it is reflexive. It is symmetric. In each case where there is an arrow going from one point of the graph to a second, there's an arrow going out of back to the first. This means that whenever one element in A is related by R to a second, the second is also related to the first. Hence it is symmetric. And you see, so here's a pair going between these two and these two. Now, you don't have to worry about this because there's nothing going in, so we don't have to have anything going out. But R, in this case, is not transitive because there's an arrow that goes from 1 to 0. So here's 1 to 0, and we go from 0 to 3. So we go from 0 to 3. It is 0 to 3 is this one. It's a little bit hard to see, but it is this one. But there is no arrow going from 1 to 3. So we found a counterexample, so this is not transitive. When we look at S, we get this as the digraph. It's not reflexive because there are no loops on 2 and 3 and on 1, in fact. It's not symmetric because you have 0 is related to 2, but 2 is not related to that. It turns out it is transitive. There are 3 cases that you have to look at, and you can verify that all of those are true. So this is transitive. So this is not reflexive, not symmetric, but it is transitive. And if we look at T, we see that the directed digraph of T has the appearance that's shown as this. It's not reflexive. There are no loops. It's not symmetric because you don't have arrows coming back, but it is transitive. The transitivity condition is vacuously true for T, and to see that, observe that we say for every x, y, z in element of A, if x, y is in T, then y and y, z is in T, then x, z is an element of T. The only way this to be false would be if there exist elements of A, the hypothesis is true and the conclusion is false. That is, there would have to be some of those. There are no such things. So in fact, this is transitive. That's an example of it being vacuously true. We have a false in the if part of the conditional statement. Now, when a relation R is defined on a finite set, it is possible to write a computer algorithm to check whether R is reflexive, symmetric, and transitive. This could be some kind of a take-home project I could give, perhaps. And one way to do this is to represent A as a one-dimensional array, like we talked about, A1, A2, all the way through AN, and use a modification of the algorithms we talked about before to check whether an ordered pair is in R. So we just do a loop that we're there. So checking whether R is reflexive can be done with a loop that examines each AI of A in turn. And if for some I, AI, comma, AI is not in R, then it's not reflexive. Otherwise it is reflexive. So you complete the loop and then you know the answer. Checking for symmetry can be done with a nested loop that examines each pair, AI, AJ of A cross A in turn. And if for some IJ, AI, AJ is in R, but AJ, AI is not in R, then it's not symmetric. Otherwise it is. And lastly, we can have a triple loop to check whether R is transitive. So we have a triply nested loop that examines each triple, AI, AJ, and AK of A cross A in turn. If for some triple this is in R and this is in R, but this is not in R, then it's not transitive. Otherwise it is transitive. And so these are algorithms that you should be able to construct and program, in fact. Now we're defining a relation T on Z, the set of integers, as follows. M T n if 3 divides m minus n. And this is called congruence modulo 3. Now, we talked about in detail congruence modulo 2 before, and we found that it was reflexive, symmetric, and transitive. Here's some logic discussions, but here is a mathematical proof. So suppose of reflexivity. Suppose m is a particular but arbitrary chosen integer. And so we must show that m Tm. Now, when you do m minus m, that's 0, so 3 divides 0, since 0 is equal to 3 times 0, and hence 3 divides m minus m, and so by definition, it is reflexive. Similar, we can, here's some of the logic that's listed, but we can test to see, is it symmetric? So suppose we have a situation where m and n are particular but arbitrarily chosen integers that satisfy the condition m, t, n. We must show that n, t, m. So by definition of t, since m, t, n, 3 divides m minus n. But by the definition of divides, this means that this is 3k, so that means that the other direction would be 3 minus k, and so it is symmetric. And the proof of the transitivity follows similarly. And so that is both reflexive, symmetric, and transitive. And soon we're going to say, oh, that means that is what we term an equivalence relation, and that will also define a partition of the initial set. But that's a preview of coming attractions. I can also ask you to test for asymmetry of a finite relation. So let R1 and R2 be relations on the set 0, 1, 2, defined as follows. And so here is R1, here is R2. An easy way to think about these is to draw a digraph of each one. Here's a digraph of R1. Since 0, R1, 2, that means that 0 is connected to 2, but and 2 is connected to 0. That is good, but 0 is not equal to 2. They're different vertices, so this is not anti-symmetric. This one is anti-symmetric because in order for this to be not anti-symmetric, there would have to be a pair of distinct elements of A, vertices, such that each is related to the other by R2. But you can see by inspection that no such pair exists. Let's test the anti-symmetry of the divides relationship. So let R1 be the divides relationship on the set of all positive integers, and R2 be the divides relationship on the set of all integers. And so we got positive integers, and this is all integers. And again, so that means that for A, B, an element of the positive integers, A, R1, B means that A divides B. And for every AB in Z, and that's the negative integers as well, A, R2, B implies A divides B. And we say, is this symmetric or anti-symmetric, and prove or give a counterexample, and we're talking about each of these. Well, R1 is anti-symmetric, and here is the example. So suppose you have A and B are positive integers, and you have A R1B and A R1A. Well, that means that B is a multiple of A, so B is K1A, and A is K2B. So that means B is equal to K1A, we substitute in, so it's K1 times K2B. If we divide both sides by b, and again b is a positive integer, so we can divide by it, we get k1, k2 is equal to 1. And since a and b are both integers, k1 and k2 are both positive integers also, and the only product of two positive integers that equals 1 is 1, and therefore a equal b, which we had to show it is anti-symmetric. Here's a counter example. In this one, R2, it is not anti-symmetric because if we let a be 2 and b be minus 2, then a divides b, since minus 2 is equal to minus 1 times 2, and b divides a, since 2 is equal to minus 1 times minus 2. So this a is R2b and b is R2a, but a is not equal to b. That's a counterexample, a proof by counterexample. Let's talk about the subset relation. So we have script A is any collection of sets. So this is a collection of sets, and we define the subset relationship, as we talked about before, on A as follows. For every u and v in that collection of sets, we say u is a subset of v if for each x in u, then x is also in v. That's the definition we had before. Well, by an argument almost identical to the solution of this, it's reflexive and transitive. And moreover, what happens is, if two sets are subsets of each other, it's true by the definition of equality of sets. So you see, this relationship is anti-symmetric. So it is anti-symmetric, reflexive, and transitive, and that's what we defined to be a partial order earlier. Last concept, I think, is, and this is a new concept right now, the transitive closure of a relationship. Now, generally speaking, a relation fails to be transitive because it fails to contain certain ordered pairs. And so to obtain a transitive relation from one that is not transitive, we have to add ordered pairs. Roughly speaking, the relation obtained by adding the least number of ordered pairs to ensure transitivity is called the transitive closure of the relation. And here's the definition of that. It's the smallest transitive relation that contains the original relation. So let A be a set, and R is a relation on A. The transitive closure of R is the relation, this is R, and that is a, looks like a T exponent, satisfies the following three properties. It is transitive, it contains the original relation to R, and if S is any other transitive relation that contains R, this one is smaller, it means that it is a subset of the other one. Could be equal to. So let's do an example where we actually find the transitive closure relationship. So we have A is equal to 0, 1, 2, and 3, and this is the relation defined on A. We're going to find the transitive closure. Well, you can look probably most easily at the digraph of this relation. So you look at that, and now what you have to do is you have to add things so that it is transitive. Now you see this is not transitive the way it is because 0 is related to 1, 1 is related to 2, but 0 is not related to 2, so we have to add that. And so we work through and we add elements until we get this one. And this, in fact, is the transitive closure of the original relationship. And we can't take any of these arrows out or else it would not be transitive. So that proves that it's the smallest such superset. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.